Okay, everybody, I'm going to cover two topics, the first of which being optimized dielectric clearances by use of a barrier system. The first way to do this, and Brad showed us this a little bit on the previous slides where he was showing field plots for dielectric analysis. There's a way to interpret the oil gaps by use of what's called a Weidmann reference curve. These have been used in the industry for many, many years now and have been backed up by lots of practical use and studies across the entire world. Now, what's important about this, you can see this is a double logarithmic scale on both the X and Y axis, showing the voltage applied, the field strength on the x-axis, and the length of the duct on the y-axis between two electrodes or two barriers. You can see, however, as the duct is increased in length, that the strength decreases. What's important to note is that the inverse of that is true. The smaller the duct, the stronger the gap dielectric strength is for PD inception. PD meaning partial discharge. Next slide, please. To continue on with some of the imagery that we had previously seen, looking at a high-low clearance. So the winding to the left, you'll see it's kind of a 2D slice through, would represent the low voltage winding. The winding to the right would be the high voltage winding. The first image is quite impractical because there are no barriers whatsoever. It's a rather large gap. You can see it's a negative 47% margin. That means at some point, whenever it's negative, that the Weidmann reference curve is the comparison of the stress across that gap to the Weidmann reference curve means that they have crossed, so that there is actually no safety margin in there. You are very likely to see an induction of partial discharge. But if we simply add a few barriers, you can go from 0 or negative 47 to a 4% margin just by the addition of 3 barriers, which is what our bottom imagery is showing. However, again, we're trying to think of these in practical standpoints. So you can't just put any size barriers in. You need to be considerate of what your design may be, what the clearances are, what the individual gaps might say. In this case, 4% is still relatively low. So if you go to the next slide, please, I will show a comparison again. So now what we've done is broken that gap up into smaller ducts using thinner barriers. So we went from 3 thick barriers to now 5 thin barriers with a little better control of each of the duct sizes. In this case, that gained us an additional 7% margin just by adding in those few barriers. Next slide, please. So the second topic I'll talk about for optimizing your insulation design is optimizing the surface stress by use of contoured insulation. Please continue. Again, similar to the Weidmann reference curves for oil gaps, there is a Weidmann reference curve for what's called an oil transformer board surface stress. We also colloquially refer to it as a creep curve because the stress, when you see a failure path, it can creep along the surface. Next, please. All right, the simple imagery here, what we're looking at is the same 2 coils with some barriers between and some 90-degree segments. Previously, we'd only been showing broken down barriers between, or broken ducts with barriers between the coils. Now we've added insulation barriers at the tops of the coils. That would go from the top of the coil up to the core yoke. In this case here, it's a 90-degree segment. You can see a kind of a thin red line with the letter B telling us where it terminates. The letter A, where it begins, would be well below the bottom of the screen there. And click next. And there we go. So what this is doing is showing us the stress accumulated along those surfaces. To go back a little bit, you can sort of see it in the top left view that's not covered. Wherever those dark black lines, what we call equipotential lines, cross the surface of the insulation, you get a charge accumulation, hence the oil pressboard interface. It's where those two touch. You can see here we can calculate the stress that is accumulated along that interface. And in this case, it's quite a low number, 14%. It's not negative, but it's still a low number, telling us that there is risk of creep accumulation along the surface of those pieces of insulation. Next slide, please. Now, what we've done is replace the sharp 90-degree interface of those insulation components with what is called a contoured piece of insulation. In this case, we would refer to it as an angle ring. There's other terminology, but Weidmann uses angle ring. What this is doing is instead of a sharp 90-degree, you're forming that piece of insulation to be an appropriately designed radius. You can adjust the radii to make sure that you are controlling the stress in the best manner possible. Next. And you can see here, just by changing from a sharp 90-degree radius to using contoured, appropriately contoured, I should clarify that, appropriately sized and appropriately contoured insulation pieces, we went from a 14% margin to a 31% margin, which is much, much safer. Generally, you're looking for a minimum of 20 to 25% margin or greater, depending on what your the needs are of the transformer, your voltage class, etc. So there's a lot of things to consider when doing this, but it should be considered to look at the contoured insulation because it can dramatically improve the reliability of the transformer.